Washer method. Do you guys know what a washer is?
Yes, it's the thingy you put.
Not what you wash your clothes with.
No, the thingy, like the thingy. I didn't say there was a washer dryer thing. God, in the hole. Stop making assumptions.
So washer, yeah, donut, whatever. You could say the donut method. Washer method. It's basically a metal disc, a little metal disc that will help help the joint, the union between, you know, two pieces of metal or two pieces of wood not wiggle, right? Yeah. So we're going to use the washer method today, and it's actually pretty easy. But before we do, let's get a good review of yesterday's. What was yesterday's? The disc method. And what were we doing for the disc method? When do we use the disc method? When you're revolving around an axis, right? And that axis does not have to be x equals, or the x-axis or the y-axis. It could be anything. But we only focused on the x-axis and the y-axis the other day.
Can you revolve around the z-axis?
Yeah, that'd be multivariable. Right. Well, it wouldn't be that bad, actually, I don't think. So anyways, what is the general formula for the volume of an object in calculus? It's the integral of the area in respect to whichever way you're looking at it, right? So it could be a of x dx or a of y dy. And then obviously your limits are usually what? Some sort of bounds, either where the functions intersect or when you graph it, you just observe that's where it ends and that's where it begins, kind of thing. Now, yesterday, the disk method was dealing with a revolution. So what kind of cross-sections, what kind of slices are you always going to see when you revolve? You're always going to see circles. And as a result, you're slicing it into infinitely thin cylinders, right? So what shape are we talking about? Circles. And therefore, what's the area? Pi times r squared dx, right? So again, there's your pi r squared, and then this is your what? Your height, right? You're taking a curve, whatever it is. So something like this. You're taking it and you're slicing a very thin cylinder out of it. Okay? And the reason, and so far, what have we represented r as? Yeah, f of x. Why though? Why was r f of x in this case? Because it's the distance from, it doesn't matter that it's the x-axis, it matters that what? It's the center of rotation, right? Yeah, half the diameter, yes. But what indicates the radius? It's the distance from the axis of rotation, not necessarily the x-axis. So the reason this is your radius, f of x is your radius, is because we are centering it around the x-axis. What if, though, we'll get into this actually when we come back from break. What if, though, we took a curve, something like this, and we wanted to rotate it about that line instead? Let's say this was y equals 1. Okay? What would the radius be then?
X minus the distance from...
So the rotation would look something like this, right? That's ugly. Something like this, right? What would indicate the rotation or the radius? The radius is no longer from the x-axis up to the curve. It's from 1 to the curve. So what would indicate, we'll call this r, what would indicate r's value? F of x represents what? F of x represents from here to here. So what's the radius? Is it bigger or smaller? So minus 1. R is f of x minus 1. Does that make sense? Okay. We're going to get into that more later, but I want to point out that your radius is not dependent on the x-axis or the y-axis. It's dependent on the center of rotation, wherever that is. Okay? You okay with that?
Yes.
Okay. So now we're going to talk about the, well, actually we're not. I said let it be 1. Okay. Let it be. All right, so I don't know if you guys want to write this down, but we've done this. We talked about this yesterday. So volume is pi r squared times h. In terms of an integral, h is represented by dx or dy, right? And then the pi, what can we do with the pi? we can factor it out of the integral because it's a constant, right? So that's your general form, assuming the center of rotation, the axis of rotation is what in this case? The x-axis, because it's just f of x is the radius. Okay, so let's take a look at this. I want you to give this a try. What is the volume if I rotate this object around the y-axis? Okay, so it's bounded by sine of x and y equals 1. I want to rotate that about the y-axis. Go ahead and give that a shot. See what you get. Graph it first without your calculator. What I want you to do for right now is graph it and then shade the region that I'm talking about. Notice it says it's bound by sine of x, y equals 1, and the y-axis. And the y-axis. So that means you're not looking at a huge piece. Okay. So now give it a try. Give it a try. You're going to revolve this around the y-axis. A lot of you guys have the graph. I could have clarified it a little bit by saying in the first quadrant, right? Yes. But there, in the first quadrant. So if I take this object and I revolve it around the y-axis, what do I have to do to revolve around the y-axis?
Go like this. Thanks, whole class.
Like what?
Like that.
How though? Like get everything what?
In terms of y.
In terms of y. You got to get everything in terms of y. That means your limits, your dy, your integrand, everything in terms of y. So, what are the limits going to be? Our bounds for our integral? What? It's going to be from 0 to 1, right? Now we can say, what is this point? What is this x value? Pi over what? Pi over 2? Okay, because that's the highest point. But I don't care about that because I'm looking at it in terms of y. So it's 0 to 1. And then what do we have to do with the sign? Take the inverse, so you're going to get what? X equals arc sine of y. All right, now I want to see your equations. From here, it should be pretty easy. Okay, the general form is the volume equals the pi times the integral of r squared d whatever. In this case, it's going to be what? dy. Because we're revolving about the y-axis. What is going to indicate my radius? So I've got this function, something like this. If I rotate this around the other side, it's going to look like this, right? So what indicates the radius? It's the distance from here to there, which is, it's the arc sine of y, right? So what's my formula then? Volume is going to equal pi, 0 to 1, arc sine y, and then squared dy. Because you have to have r squared. So you see it, there's your pi, there's your r squared, and there's your h for the cylinder, right? Are we okay with this? Yeah, if you didn't type in your calculator, do so. Just like that. Just use x. You can use x. Just make that x, make that x. No big deal. Do you guys hear that? Now that you have the equation, there's no difference between this and putting x's here for your calculator, just so your calculator can do it. Okay? So do it if you didn't do it.
Okay.
1.468? Right? And we are talking about small numbers here, right? Now, we can compare and see if this makes sense by using the volume of a cone. What's the volume of a cone? 1/3 pi r squared times h, right? Now this isn't a cone, right? But let's assume that it was. Instead of that curvy thing, it would be a straight line here, right? So when I find the volume of the cone, is the volume of the cone going to be bigger or smaller? Okay, whatever. It's going to be bigger. So what would in this cone, the cone is static. In other words, these sides are just flaring out at the same rate. What is the radius of the cone? What's that radius? It's pi over 2. This is a radius of just the generic cone. What's the height? 1. So we'd say pi times pi over 2 squared times 1, and then we have the 1/3 out front. So that's going to be pi cubed over what? 12. Type that in your calculator and see what you get. Again, this is not calculus. This is just geometry. And I'm showing you how the volume of that is going to be smaller than this because we cut out a piece.
2.5.
What?
2.58386.
That can't happen.
2.585.
Okay. I'm sorry, you're right. 2 point what? 584? Okay.
8386.
Okay.
But I like it. That should be perfect.
So, and we can see, actually, this is pretty significantly bigger. It's a whole unit bigger, whole cubic unit. And you can see this sliver is being cut out, but it's being cut out all the way around it. So it's having a pretty big effect on it. Does that make sense? Okay. Are we good with this? Do you guys understand it? It's just the volume formula of a cylinder. Why a cylinder? Because we're making circles when we revolve. Okay. Let's take a look at just generic geometry, see if you guys can remember this. This will help you understand this. Okay. So if I have a cylinder, see if you can picture this. See it? See it? Can you guess what it's going to be?
Toilet paper.
Toilet
Used it
paper.
on this, to be honest with you, Mikey.
I don't remember it.
But like you spend
These are a couple of years old now, so I probably spent at least a couple hours normal. Like this kind of thing probably took me 4 hours to prepare. Not this particular slide, but the slide altogether. Okay, so we have a roll of toilet paper, and we want to figure out the volume of toilet paper, and you got that little cardboard thing inside taken out, right? So, okay, fine. It's a big circular thing, and we're drilling a hole in it. Whatever it is, how do you find the volume of that? You take the volume of the big guy and subtract the volume of the little guy. Now I want to check your number sense here. Do you think that the volume of that inside thing will be equal to the volume of the remaining thing, basically?
Oh, well, if it's 2, 2.
It's 2, 2. Do you think that that volume of that outer washer, in a sense, is the same as the volume of that inner cylinder? Well, let's find out. What are the conditions? There, those units.
okay.
Just in this case. Okay. So the volume of the first guy, the volume of the big cylinder is going to be what? Pi r squared times h. What's r? 4. Okay, r is 4. All right, come on. Be done. So the outer cylinder, and we're going to use these terms, outer and inner here. The outer cylinder is pi times 4 squared times 7, which is 112 pi. What's the inner cylinder going to be? Pi times 2 squared times 7, which is 28 pi. Now, how would I find the volume of the actual object? We're going to subtract those. So the actual volume is 112 pi minus 28 pi, which is 84 pi inches cubed. So the answer is obviously, is the volume of the thing we're talking about here the same as the volume of the inside? No. Do you guys know why? Think about it. I mean, look at it. The further you get out here, the more 2 inches has an effect because you're going around in a bigger space, right? In fact, I would argue, what did I do to the radius of the inside thing to get to the outside thing? I doubled it, right? If you're thinking dimensions, if I double the dimensions, I'm actually multiplying it by 4. 2 squared is 4. So if I take this and I square it, I'll get my original whole thing. Or not, I'm sorry, take this and multiply it by 4, you get that. That's beside the point. The main point is, what did I do? I took the volume of the outer shape, or the outer solid, and I subtracted the volume of the inner solid, right? Okay? So let's expand on that, or let's try and simplify it a little bit. You guys agree that this is the case? The volume is equal to pi times big R squared times h minus pi times little r squared times h. Okay. R, big R meaning the big radius, right? And then little r meaning the inside radius. What do they have in common, both these formulas? Right. Notice the height is the same, right? And pi is the same. So I could factor those out, and you'll see why in a second. Okay. Why didn't I factor out the h? In calculus, what is the h represented by? The change in x, the dx, right? And where's the dx in your integral? It's in the integral, right? So you don't factor out the dx outside the integral. You can factor out the pi, though, right? Okay, so let's take a look at what this looks like in calculus, okay? The washer method. So the idea of the washer method is basically taking a circular object, a spherical object of some sort, and cutting something out of it. Another circular thing, cutting out of it. Okay, so geometrically, it's not a difficult concept. You just have to know what it does to the integral. Okay. I want the region in the first quadrant enclosed by the y-axis, the graph of cosine of x, and the graph of sine of x. It's going to be revolved around the x-axis. Find the volume. So again, graph what I'm talking about here. It's important. It's bounded by the y-axis, cosine of x, and sine of x. I should be able to graph sine of x and cosine of x without a calculator. Or the rest of the curves so that you know you're looking at that. And then try, once you got it, this is why pencils are good, because we're not going to look at the whole graph. We're only looking at a piece of it. Erase what else we're not looking at. And then try and revolve that thing around the x-axis. No, it doesn't. It's pretty cool. It says around, you're revolving it around the x-axis. Did you guys get that as the region? Okay. Let's take a step back real fast, okay? Let's take a step back. I want you to find just the area bounded by those two curves. Just find the area. I don't want the volume right now. Just the area. How would you find the area? Don't say first minus second. Say upper minus lower. So what's the upper function? So figure it out for me. Set up the equation. Just the area right now. It's good to compare the area equation to the volume equation. All right. So what's the area? Area is the integral. Well, let's get the integrand first. Of cosine of x minus sine of x dx. And now what's our limits? 0 to wherever they intersect. They intersect when cosine of x equals sine of x. So you could just think about when that happens, or you could divide by cosine, so you end up with what? Tangent. 1 equals sine x over cosine x, or tangent. So when is tangent equal to 1? Pi over 4. So x equals pi over 4. Okay, so pi over 4. And then anybody do that? Anybody get an answer? You get the calculator. Okay. What'd you get? Point what? 0.414? Okay, cool. That is the area, right? We didn't revolve anything. That's just finding area two-dimensional. You guys okay with that? Yeah. Okay. Now, we're going to revolve this. So watch the screen. We're going to revolve it. How do we draw a revolution? For those that are having a hard time with this. What am I going to do? I take that, and I reflect it down here, and then I just connect the pieces with a bunch of ovals or circles, right?
The dog bowl.
So it's kind of like a dog bowl, I guess you could say, right? Okay? You guys okay with that?
Yeah.
Now, we can go through this and try and understand it piece by piece, and maybe that's a good idea. But what function represents the big cylinder that we were talking about before? Which function does the upper, this piece, the cosine or the sine, represent the big cylinder as I go around here? It's like the toilet paper thing. You're taking the volume of the big one minus the volume of the little one. The cosine is the bigger piece, right? Okay. So I'm revolving it about the x-axis, so the radius is just cosine. What's the radius of the little piece, the inside? sine. Okay? So we should be able to see, just to kind of get an idea of what the cross section looks like, right? Can you see the cross section? Do you see the washer?
Yeah.
The circular thing with the hole, right? So how do we find the volume or the area of the washer? Because remember, I want to leave this up here because I want you guys to see the comparison. But remember, volume is equal to the integral of
Bounce.
the area times dx, right?
Yeah.
So what cross section do I have? I have a circle. I have a washer. The shape is a washer. How do you find the area of a washer?
Subtract it from the one to the other.
You find the area of the big guy minus the area of the little guy, right? Okay, so let me separate this. This might help out. How would I find the volume of the outer shape? So just looking at this piece, the cosine, right? What's that going to look like down here? It's going to do this, right? Let's do something like this. Well, there's no hole in it here. So it's just a solid mass. So what's the volume of this guy? It's going to be the
Cosine?
pi times the integral from 0 to pi over 4, because that's where they intersect, of cosine of x squared dx. Again, there's your pi, there's your r squared, and there's your height, right?
Yeah.
Now that is the volume of the solid piece. And then what's happening?
You have to subtract.
I'm cutting out, I'm scooping out what's the sine part. So now, what's the sine part look like? It's like this.
Is
You
it
get that?
cone?
Kind of, but it's arced. It's not a straight line. So what's the volume of this guy?
Pi into 0 to pi.
0 to pi over 4 of
Sine squared.
sine of x squared dx. Now what are you going to do to simplify all that? So the volume of that guy that's in the screen is minus that, right?
Okay, so the disk method is circles and the washer method is subtraction.
Yeah, well, the washer method is circles still. It's just you're taking the big circle minus the little
Circles
circle.
plus subtraction.
Yes.
Addition by subtraction.
Addition by subtraction by subtraction, because we're removing. Okay, but I want to try and put these together using our rules of integrals. This will help us quickly figure this out. Instead of actually having two separate integrals and subtracting, what do we notice about both these integrals?
Oh, just pi.
They have the same bounds, the same limits. So how could I rewrite this? Pi times the integral from 0 to pi over 4 cosine of x squared minus sine of x squared dx.
So the difference is the squared and the pi? Between the area and then the volume?
Okay, I see what you mean. So if you're looking at the area, it's just you're subtracting the upper minus the lower, right? Well, volume is kind of the same thing, but what do you do with the upper? The upper is represented, what does the upper function represent? The radius, so we have to square it. So they look very similar, but you got to make sure when you're talking about volume of a revolution, you got r squared and r squared. Okay, let me take it a step back. If I wanted the volume of just a basic cylinder, volume of a basic cylinder with a piece cut out of it, it would be pi times big R squared times h, right? We said that? Minus pi times little r squared times h. You know what I'm saying? So we can factor out the pi, and then we can write it like this. And then we factor out the h over here. You see that?
Okay.
So can you see how this is the same as this?
Yeah.
You got pi factored out front, you got the h factored out back, and then you're summing up the integral because you're adding up all those little volumes. Does that make sense a little bit? Okay. So what did you guys get? Did you get an answer? 0.500 something? I don't know. I got 1.571. If you do not see it in the simplified form, if you do not see it like this, it's okay. You can separate the integrals, find the volume of the whole thing, and then minus the volume of the little thing. There's nothing wrong with that. It's just a lot more work overall because you have to do two separate integrals, then you have to subtract, and it's just a mess. It'll work, but it's not as convenient. Like that, you shouldn't need to. This, taking the antiderivative of that would be tough. So it's more than likely a calculator problem. Okay, so in general, if R represents the big radius and little r represents the little radius, what's the general form for the volume? Pi times the integral from a to b, f, whatever the intersection is, of big R squared minus little r squared. And then dx or dy, depending on what you're talking about, right? So this is revolved about the x-axis, okay? Or horizontal line, I should say. And notice this is important. This is not the same as the integral of big R minus little r squared. A lot of students on the AP exam fall into this trap. They want to try and simplify it, so they just say big R minus little r and square it. Because they remember the area was basically big R minus little r dx, right? And so they're thinking volume. It's like, okay, volume. I just throw a square there and a pi there, and I got volume. No. Is this the same as this? No. What would I have to do with this? This has to be r minus r times r minus r. Then you have to FOIL it, and you don't get this, right? So be careful with this. You've got to separate it as the big radius squared minus the little radius squared, because ultimately we're finding the volume of the big thing minus the volume of the little thing. You okay with that? Okay. We're going to try this one. So the region bounded by y equals e to the x, y equals 3, and the y-axis, so that's your region, and you're revolving about the x-axis. So you should have gotten, that is your curve, right? E to the x is exponential, right? The more you go over, the quicker it steepens out, right? The quicker it increases, okay? So we're looking for that object being revolved around the x-axis. So here's a good way to look at this, okay? Which function is furthest from the axis of y equals 3? So we could say this length here is the what? That's your big R, right? That's your big radius. Okay? Now, is that radius changing size at all? No, it's not. It's a constant. The inner radius, this represents your inner radius. You get that? But is that radius changing size? Yes, it is. But what represents the distance from the axis of revolution and the curve? E to the x. So we would say something like this. We would say big R, maybe I should write this down up here. Big R is what? What's big R? 3. What's little r? E to the x. Does that make sense? Okay. So what's our general formula? Volume equals I times the integral, whatever, of big R squared minus little r squared, what, dy? dx. What's my limits? 0 to what? You got to figure out where they intersect. So we would say e to the x equals 3. So what's x? X equals the natural log of 3. So that's my upper bound there. You guys okay with this? And so now I'm going to substitute in 0 natural log of 3 of 3 squared minus e to the x squared dx. And then pi over. Can I simplify that at all?
Yeah.
y times the integral from 0 to natural log of 3 of 9 minus what? E to the 2x. Yes. There it is. Could you have done this a different way? Yes, you could have found the volume of the cylinder that has a radius of 3. You could have found that volume. And then you could have found the volume of this funny shape. What's the radius of this guy? The radius is e to the x on this guy, right? Is the radius constant in this function? No. So that's why we use a function to represent the radius. What's that? No. Three to the second to the fourth. What's that, right? Now we have. What? Yeah.